much. So the first talk will be by Joachim Brietner about inspection testing.
Thank you. Yeah, I'd like to do this talk. I'm trying to coin a term. The term is inspection testing. But before I get to explain to you what inspection testing is, I want to tell an anecdote. And the anecdote begins with Matthew Pickering giving a talk at IFL about generic lens a year ago. Now, this isn't Matthew Pickering, this is Tom McKiss, and this is IFL, this is ICFP a few days ago, but it's the best picture I could find. It's like almost Matthew Pickering, it's almost IFL. It conveys the idea. But it's about the same work that ended up getting them to ICFP with the generic lens. And they were presenting that already, first version, at a small workshop in Bristol, IFL, very nice done workshop, by the way. Thanks to Nick, who is here. And so what is generic lens? Right. I assume most of you know what lenses are, and if not, I'm sure you can tag along with an idea. They created this library to create a lens out of thin air whenever you need it, using generic programming and type delimitation. So you have some data type, let's say an employee type with an age field, and you say, oh, now I need a lens that reaches into this employee type and gets the field. And rather than writing the lens by hand, as you might have done a while ago, or maybe using Pascal to generate them when you define your data type, you don't have to do any of that ahead of time. You just say type int, and it gives you a lens. And as I mentioned, it uses generic programming and type delimitation. So what happens under the hood conceptually, or I think also practically, is you have your concrete data type, and it turns it into its generic representation. So it's replacing the concrete constructors that you wrote in your type with the generic ones, of which there are only like a handful of them, sums and products and constants and these things. You've seen some of that earlier today. And then on the generic representation, it uses type family and type classes and all this cool GHG magic to traverse the data type to find the field that you're interested in, and then do whatever the lensy thing you're trying to do, like update. And then it takes this generic representation and turns it back into your actual data type so you can continue with your project. And I read about this on Reddit, and I saw the talk, and I was a big fan of it. Like this is what HASP is about, really applying high-level ideas and creating new abstractions and writing elegant code. I was very fond, I'm still very fond of this work. But I wouldn't want to use it. Can anybody guess why I would not use generic lens? Performance. Yeah, all the handy stuff that I just described, taking this possibly big data type that you wrote, converting it into the generic representation, doing all kinds of stuff there and going back. That can't be efficient. I mean, we're used to not having C-like performance, but really, no, that didn't feel like I would want to use that. So at the end of the talk at IFL, I asked Matthew, so how bad is it? How much are you paying for that? And he said, oh, nothing. It's just as fast as the handwritten version, because GHG optimizes it all the way. And I didn't believe that. And I know a little bit about GHG. So I thought I had reason to believe, that this is out of reach for not twice as fast. So, but they not only had the talk, they also had the paper at the proceedings. And I looked at the paper, and in the conclusion they wrote that the author will have the confidence that the abstraction will be without cost and the flexible, yeah, that's it. The abstraction will be without cost. So they even dared to put it in the paper. And also in the paper they described how they come to the conclusion. And it's a very convincing argument. They wrote the manual version of the lens and the generic version of the lens, and they compiled it both. And they asked GHG, please tell me what you think of this code after optimization. And they compared it, and they said, oh, that's the same. That's an argument I would buy. But I still didn't believe it. So I did what most of you would do in this situation. I sat down, and I opened a little example. So I guess I need to make this a little bit bigger. Is this readable? Wait, this is this is the wrong proportion. Oh well, we'll deal with it. So I'm not going to explain lenses here. This is not a monitor, sorry, this is not a lens tutorial. But here we have the manual lens, and it does some boilerplate stuff. It's always going to look the same. It's boring to write. And then here's the way of using generic lens. You just say type in, and it reaches into the Sailor type, finds the field of type int, and produces the lens. So I have this file with the two variants, and then I compiled it. And I guess I should make this maybe, yeah, that's probably better. So this is a time capsule. So we use the GHG 8.2, and we optimize. I'm not going to cheat you. The file, and we also want to use the right version of generic lens, which at the time of writing, or of trying, I guess, was 4.0.0. And then we also want to ask the compiler to tell me, please, the simplified output, or the simplified code. And then we also want to suppress some additional stuff that it just would make the output too big.
Does this do these suppress all?
Yeah. No, I don't want to suppress all. I don't want to cheat too much. And it's going to be big, so I'll put it in less. I'm missing something, as always. But that's fine. GFC tells me what to do. And GFC tells me even more what to do.
There's a space missing at the end.
So press is 2 Ps.
There you go.
Thanks. Okay, so let's look for the manual lens. It's there. So this is what GHG does out of the code. It looks similar. There's fmip, there's lambda, there's some elaboration of types. Nothing unusual. So this is the manual code. And this is the generic code. This is how it begins. This is how it continues. The generic code. And there's more of it, and we can scroll. And maybe we can go page by page. So this is not page by page. Let's go to generic lens, and at some point it was lambda. Okay, and we're done. I was right! So I did whatever I would do. I would go to GitHub and write a passive-aggressive issue on it. How can you claim these things? They're not true. And then Matthew said, somewhere down here, well, it used to be true in 0.2, and Songbird, what did you break? And then Songbird looked at it and said, oh yeah, I broke this, and I fixed it. And he uploaded a new release, and if I do the same thing, and I change, not the suppressed things, I got them right, 0.4.0.1, we can again look for the manual version, and it's there, it's unchanged. And here's the generic version. The GHG not only makes them the same, and then also notices that they're the same and just makes them equal. Okay, now I was convinced. But let's step back a bit. Something went wrong. At some point in this process, we were missing something. And I think I made the point pretty clear at this point what we're missing. We're missing a way of making sure that these promises we're making about the libraries are actually true. So Matthew checked the promise. He didn't lie out of malice, I assume. And he checked it with 0.2 of his library and maybe GHG 8.0, 8.2, who knows, and it was true. And the way he checked it wasn't the way I did it. Write some examples, look at the core, looks good. But that's too tedious. It's too manual. You have to manually inspect the results of the presentation. And because it was too tedious, he didn't do it again when Songbird improved the library in some way. So what we're missing here is, and that's the term on the coin, I'll find the slides again, inspection testing. And here's a definition that I propose for this term. Inspection testing is an non-functional property of a compilation artifact of a specific piece of code specified declarative by the programmer and checked during compilation by the compiler. Let's break it down a little bit. I care about non-functional properties here. Because if it were functional properties, or something that would affect the behavior of the program, then we just use testing the way we did it the last decades, and there's plenty of great methodologies there, especially in Haskell, as we have seen in my talk on Wednesday. So this is about non-functional properties. And notice that the promise of generic length, the generic version looks the same after compilation than the manual one. You can't see that when you run the program. It behaves the same. So it is a non-functional property. I'm focusing on compilation artifacts, which is either the intermediate language, some intermediate representation, as we've just seen, or maybe the final assembly code. This excludes the source code, because if it's just a property that you can see directly from the source code, then you're in the realm of syntax checkers, linters, external analysis tools. We have plenty of those. We don't need more. Well, we need more of them, but that's not what I'm trying to do here. It should be a property that's of a specific piece of code, or maybe a specific class of functions. And not, see, most of these are defined by what they're not every code in this language. So for example, Haskell, unless you try really hard, is type safe. This is a property that you can prove using program exploration and all kind of technical stuff. And there's no point in testing that because you've proven it. Or for example, if you're writing C programs, then the linker will ensure that once you've linked your program, there are no unresolved symbols anymore. This is not something you can prove, but this is something that's being ensured by the toolchain. So again, you don't need to test it, it's just true by construction. Whereas I'm looking at things that they're only true for certain pieces of code, because not every Haskell function you write is equal to the manual length value. The property needs to be specified. I point this out because I know that some people in this room, including me, sometimes we look at the core output and we look through it and we think, is there anything that looks fishy? And we don't find anything fishy, that's fine. That's useful, but we can't mechanize that. We can't mechanize intuition about this looks like something I need to investigate. So we need to think about, okay, what is the property we care about? And in this example, the property we care about was it looks like the manual version. Easy to come up with. Once we have the property, maybe we want to have a way of declaring it in a declarative way. And I put this into the definition to contrast it from properties that you, and this is a bit vague, but that you check by implementing a complete new pass, a complete new analysis. So static analysis is a thing, but it's usually you're implementing something very heavyweight. I'm looking for lightweight ways of specifying this is my intent. Dear compiler, please tell me if it's wrong. It's already useful to declare these things, even if we don't check them. And I have an example for that. We'll come back to that in a moment. The data text module, which I assume many of you are using, has a feature called fusion. And fusion means, in this case, if you write a pipeline of these functions, then if you're using the right functions, it will fuse them into one thing, and there will be no more intermediate text values around. It's a promise that is being made in documentation. And then if you look through the documentation, you can see actually there are lots of functions where it is declaratively specified. Oh, all the shades are disappearing on this projector. Like this is gray. Anyway, for these functions, it promises that fusion will happen. And this is a declarative specification, but it's not being checked. It's just in the documentation. And we'll come back to it. Okay, and another important bit of this definition is that it should be checked by the compiler because we care about what actually happens to our real code as we compile it, and not to what might have happened to this code if we had compiled it in a different tool, for example. So this is what I call inspection testing. And I mainly motivated by the example with generic gens, created a library for Haskell that is called inspection testing. And we can use it in this example. So to step back one step. Let me go to this file. So let's say we want to use, let's do some wishful thinking. If we could wish for the best possible world, how would we be able to specify our intent here? Well, in the best possible world, I would expect that I could write a language extension that says, okay, this code I also want to use the inspection language extension, inspection testing extension, and then I can say inspect the manual version is the same as the generic version. And that's all I would want to do. And then the compiler checks this for me and is happy. Now, in order to do it this way, I would have to be able to modify the compiler. Turns out I am, but it wouldn't be the right thing to do because then every user of this feature would have to need a fork of the compiler, or we need to convince Simon that this is important enough to be in the compiler itself. So the next best thing then, this visual thinking, is to pretend that we can do these kind of things, like extend the syntax and extend the language, and we can do using plugins. So what you can really do, instead of saying language inspection testing, you say language template Haskell, and template Haskell allows you to fake syntax in a way. And then you import submodule test inspection, and then we have this inspect combinator, but we have to use template Haskell syntax, so we use quotes around the names, and this compiles. And we can actually now run it. Let me remove the debug symbol and compile it. Nothing happens. It's great. Has been checked. Or has it? No, it hasn't. I didn't load the plugin. I mean, that's the downside of having it not properly integrated. There are these pitfalls. I have to say options GHC have plugin test inspection plugin. Sorry. Get this here, and I compile, and it says, oh, I found this application, and testing was successful, and great. And you can do the cross-check, what happened if we were doing the old version. And it says it failed, and it gives us the left-hand side and the right-hand side, basically the same as it did before. It doesn't make it any easier to make sense of this than we're being told about it. And now it's super simple to test these things. So I can, for example, say, okay, let me vary the compiler version. And it's just two key presses. I've checked the completely new compiler. And it's, oh, interesting, the new released version fixed it with 8.2, but not with 8.0. But because the generic Glitz authors were now starting to use inspection testing, they could test these properties on all the compilers they care about in parallel, and then the next version that they release actually fixed the problem on their old compiler, and now it works there as well. And it's part of their test suite now. So no more broken promises. Let's see. Oh yeah, we skipped this part. Well, we can do this different order. So I gave you this definition for inspection testing. And here's basically a brainstorming list of things that might qualify as properties that we want to do and want to have inspection tested. And we've seen the one where we check two versions of the code to be the same. Maybe we want them to be the same, but up to types, because types don't matter that much for runtime, so maybe equivalence. We talked about fusion. That's something that many people wanted. Being able to test whether some code is free of any type class overloading. And that was actually contributed by someone after I gave the talk at Zurich, so that's cool. We have that now. If you write high-performance Haskell code, you usually care about that there are no allocations in a loop. So that is something that's an inspection testing property. And then there are more ideas that I haven't implemented yet, but are all interesting. In particular, absence of branches is not performance. So this is not just for performance. If you care about security, you want to make sure that your code has no dynamic branches depending on SQL inputs, so that there are no sidechain attacks. or maybe hopefully less, or none, or who knows, nobody knows. Anyway, it helps with a lot of branches. Okay, so we've seen this, and basically this is a summary of how we now encode these properties that are had on the slide in the code, so we can ask for equality, we can ask for other things. And let me, in the final interesting remark, come back to this fusion example. So we've seen this documentation, and if we look at the data text documentation, we see that the subject to fusion string occurs 49 times, and I think 2 times was in the header, so it's 47 functions that are supposed to be subject to fusion. So we can easily write, show how that would look. Got it now. Oh, it doesn't have the property. But anyway, we can write a test file that has one of these pipelines, and then we can use inspection testing to find out whether fusion happens. And that's good if I want to know if this particular example fuses, which is useful because it's example in documentation, and it's embarrassing if it doesn't. I will not demonstrate it in the interest of time, but spoiler, it doesn't. But now there are 50 functions in the data text module, and then another 50 functions in the data text lazy module. So doing this manually, even though we made it much more easy by introducing this inspection test library, doing that very function would still be very tedious. But we're building on Template Haskell, and Template Haskell is a better programming language. So what we can actually do is we can scale it up another notch and generate these test applications and test them very, very quickly at the same time. So, so I wrote a little package that looks at each of these functions and creates a bunch of, I think, 4 or 5 pipelines involving this particular function and another function that it knows are behaving well. And it's telling us whether the mutation set it was fusing, and then the other two, ignore that two, whether they actually fuse. We see that it mostly lines up, but for example, reverse is documented to fuse and doesn't fuse. So we can find these broken promises very efficiently now. And we can even do almost quick check-like stuff and generate, because fusion is something that happens between 2 functions. So maybe take always fuses and take while always fuses, but if I put them together, they don't fuse anymore. And now we have a combinatorial explosion, and doing that by hand would completely bogus. But we don't have to do it by hand. We can just generate 1,000 random text pipelines that have the right type, and run them through this tool and find out whether they fuse. And length.const.snot.peg is supposed to fuse, but doesn't. And then in the end, we come to a conclusion that says, well, in data text there are these 11 functions, I think, that could fuse but don't. There are 2 that are not documented to fuse, but they do. So we find out and then data text lazy is a similar image. And right, here's the final slide with some quotes which you can read while we have questions, and I'm happy that more and more packages are using it. So besides generic lens, there's fin and vec and generic SOP and HKT and prospect and something I wrote that use inspection testing. And I hope that you too will now think about where do you in your programming make promises of that form. And maybe you want to sleep well at night. Use inspection testing.
Right, great talk. I was wondering, it was not clear for me the promises. They depend only on GSC core, or you can say if this term has this type, don't check anything. If this term has this other type, then you should check for a promise. Can you do that?
Can you say that again?
Right. So imagine you want to check that you don't branch on secrets, right? And there are some pieces of the program that use a security library that you don't, if that program was built with that security library, you don't need to check for anything. But if there are some other pieces which are not, then you want to check that you by mistake you didn't branch on secrets.
Okay, so I guess maybe the question could be rephrased. How can you make these test obligations more expressive into like this particular part of the program I care about?
Well,
and that's.
I mean, what is the input of your is GSC core, or I can use types, or what is the dependency?
The implementation for all these properties so far is basically a Boolean function on core. It takes core and returns a Boolean function.
Right.
The methodology could be extended to also look at C minus minus, for example, or assembly.
That's right.
But right now, all the things that inspection testing the library can do is properties on core.
Right. Okay, thanks.
Yeah, simple question. In the results of fusion inspection, you had question mark. What does it mean?
Good point. I found that the singleton function was behaving very confusingly. So if you, singleton just returns a single text with one character in it, and it would make, there were functions that were supposed to fuse, but they wouldn't with singleton, and there were functions that normally don't fuse, but when you put them in singleton, they maybe become a singleton themselves, and then they fuse again. So basically the three columns were what is documented, then what is predicted by my understanding of what actually happens, which is like a simple function says, okay, if all of them are fusing, then yay, if one of them is not fusing, then nay, and if singleton is there, I don't know. And then the last one is what actually is being observed. So in my modeling of reality, I said, okay, singleton, I don't know, it's speculative.
Right, so but you only go beyond, like, can you do non-functional properties, like counting the number of function calls it makes, or number of recursions, or stuff like that?
So I guess the question is, what about dynamic properties that you can only observe at runtime?
Yeah.
For some reason, I've mainly ignored them, both in the implementation as in the definition. And it's maybe a question of further debate whether there's room for a dynamic inspection testing library in parallel. Maybe I'm just too deep in the type checking community to think about dynamic type as something that you still don't use. Like I think do these things directly. But I think in principle that might also be useful.
So you use a combination of template Haskell and a PHP source plugin to make this work. Is template Haskell essential for this, or would it be possible to implement this as like have a comment that the source plugin will pick up?
The template Haskell is really just syntactic sugar. What it does is you say inspection this and this, and it takes the obligation, which is data type, and attaches it to the module as a module annotation. Module annotations are a mechanism of THD to transport data from the source to some plugin. And by the way, it's a core-to-core plugin, or a source plugin, but it's not very important. And I found these annotations are slightly unwieldy, so this is a very thin convenience wrap around it. I think you still need template Haskell a little bit for the quotes, like to refer to I don't know, let me show it, but you have to put a quote in front of the name to get the name, and I think the module annotation mechanism is related to the template Haskell mechanism and shares the same way of getting a name into the data. So you don't, like if you hate template Haskell completely, then it's a bit annoying, but you don't have to, you can avoid the inspect function if you want for some reason.